I'm Samuel Como, and before we start the session, I just wanted to share with you guys, for years I've been trying to come to Spain. Man, getting a visa from my side is like such a pain. So finally, other people like Nimish, I don't know if you guys know Nimish and you've seen the design guide session on NSX. If you haven't, you should check that out. In the past years, he used to take my place in the last minute, but I'm glad I'm here with you all today. So today's this session, thanks for joining, and this session is focused on NSX performance. But before we start, how many of you have attended this session in the past years, like NSX performance? Okay. And how many of you have NSX installed? Okay, awesome. Okay. NSX for vSphere. Oh, no, man. Please. It's time, okay? So how many of you are on 10 gig networks? 10 gig, okay. 40? Okay, 25. Okay, 100? Oh, man. How many of the 100 gig ones are in the telco side? Telco, okay, 1, 2. Okay, awesome. All right, so this session, we're going to kind of look at general purpose computing. And as you've seen in this crowd itself, right, there are some niche application types that require a little bit different type of handling, that is on the telco side. But for most of the applications what I'm going to focus on, for most of the applications, right, what comes by default and what can you expect, the kind of performance that you can expect from it, right? So that's what we're going to focus on. I'm a senior technical product manager in VMware NSX, that is Networking and Security Business Unit. You must have seen this many times. Some of the things that we talk about could be future, and just keep that in mind. With that, from an agenda perspective, we'll go through an overview of what the NSX platform looks like, and I know some of you, I was just trying to meet some of you folks earlier, and I know some of you folks, you're curious, what NSX is about, and some of the other folks are very senior in terms of experience with NSX-V and NSX-T too. So we'll touch a little bit on the intro kind of items, and then focus more on the types of applications, what do they, what kind of requirements they have, what kind of hardware requirements do they have, and so on. And then we'll talk about how do you tune for performance with different types of applications. And finally, some design considerations, and with what matters most for you. With that, one of the things that we noticed today, right, is there's a huge need, with the public clouds, there's a huge need, people need that same efficiency of public clouds where I should be able to click, and get what I want, and really fast, right? When you look at the workload today, the speed at which the workloads are deployed, you need the same, you expect the same speed from networking infrastructure and security. And when you're moving these workloads around, you don't want I moved it and then I don't know what the security posture is anymore, right? No, so you want that security posture also to go along with wherever that workload is applied. And NSX basically addresses all of these requirements, right? Efficiency point of view, the speed of deployment, matching whatever your workload speed is, and so on, right? So, and be able to scale across multiple different domains. That's where NSX shines. And how does that do that? So, by the way, I'll have these markers throughout the deck. Basically, those violet markers are sessions with additional details on those particular topics. Now, all of those sessions are pointing to the ones in Vegas, simply because there's a wider variety of sessions, I guess, in Vegas, and I didn't want to have one in Barcelona, one in Vegas, and stuff like that. But just make a note, those sessions will help you get more details on all of these items. With that, for those who are new to NSX and you want to know what's going on with this, right? Very quick intro. There's better sessions that actually dig more into the details of these. You have these ESXi servers. The way we enable all of the functionality that it comes with NSX is basically by creating these segments. And you can have, just like a VLAN backed segment, right? This overlay backed segments, you can have VMs on top, you can have firewall rules that protect those VMs. And the way these VMs would communicate is before those packets exit out of the system, they are encapsulated or decapsulated. In NSXT case, it's Geneve. In the NSXV case, it was VXLAN. Geneve because you have more flexibility in terms of what you can add onto that header. So we kind of went with this route. And once it is encapsulated, think about it, every packet is encapsulated, so there is a cost to encapsulating that packet. And that cost is, in most cases, okay? If you guys are aware of what kind of cards, NIC cards you have, let me tell you, almost every single NIC card out there would support a way to offload that cost. And it basically is done at the NIC level, and then it's sent to the other side, decapsulated, and then sent to the VM. So this is basically the overlay, right? Intro, a very, very short intro to the overlay and how that works. You can have multiple segments, and the path is the same. The only difference is, in this particular case, there's routing at source, so that if that packet needs to go to a different segment, it's already routed on at source, and then it is sent out across the network to the next side. Now, this is what I would refer to as east-west traffic, or the compute side, or the workload side traffic. And there are certain things that you would need to enable optimal performance here. For example, in most cases, Geneve offloads, Geneve RxTX filters, and RSS, and so on. How many of you are aware of Geneve offloads? OK. RxTX filters and RSS, probably the same crowd. OK, 3, 4 people. OK, good. All right. So, and then you also have, you can also leverage DPDK. How many of you are aware of DPDK? What is that? OK, good. All right. And then this is within the compute system, right? When you want these packets to exit your NSX domain, that's where we have the edge gateway, where you can have multiple different functions, routing, firewalling, and whatnot, right? And if you attended some of these security-related sessions, there's a bunch going on here, but that basically is your path to exit from the NSX domain. And it's the same process here, except for one difference. The difference is, in the previous case, the encapsulation and decapsulation happens at the ESXi host level, versus when it comes to the edge VM, the VM itself does the encapsulation and decapsulation. It's not at the host level anymore. Okay? So you encap, decap. Why does it matter? It matters because you know where exactly that process is actually happening within this whole tree, right? And then after that, you send it out. So basically, this is what we call the north-south direction, and that's where, or inside and outside NSXT domain, and that is where you would need RSS or DPDK to enable higher performance. Now, all of these terms, right, that's what we're going to dig into over the next let's say 35 minutes, but this is just a high-level overview of what all you need and where do you need those things. With that, let's take a look at data path options. We have 3 different data path options, and if you don't know anything about these data path options, there's a high chance that you're actually on the standard data path. The standard data path is basically interrupt-driven processing. That is, whenever a packet comes, It'll say, hey, I've arrived, and then this data path would process that packet. You have some advantages like TSO, LRO, and things like that. Almost every general purpose application today can leverage this, and you're all good. Except for one or two people that we were talking about, telcos, right? Telcos, NFVs, and things like that. In this room, there were, I think, two who focused on that. So that is a percentage even outside, too. Like we see 99% of the folks are actually on this standard data path, and it works perfectly fine. But for those who are slightly ahead of this curve because of their application types, for them, enhanced data path is another stack that actually does the processing a little differently. In this case, what happens is, instead of a packet arriving and then basically saying, hey, I'm here, process me, right? The processors are actually checking to see whether there's any packet has arrived. And this is a DPDK format of packet processing, right? And you have a couple of options there to standard or performance. Based on the requirements, you can choose one of those. And finally, we have these SmartNICs, which basically take off all the processing and put it down at the NIC level. So anyone trying out SmartNICs? The same telco folks, most probably. So when you want to save CPUs and really get the highest performance, then that is where you land, right? Like with the SmartNICs. Again, I want to be sure you all get the picture here. This is for very unique applications, and again, 3 in this entire room, right? 3 in this room are actually at this field where they need that for their applications. In most cases, your standard data path would help you handle most of this stuff, and I'll explain why. Which leads me to the next part, which is the application. Again, there's a session if you want to dig into the details of SmartNICs. I'll use a lot of this truck and fast car analogy because often, just imagine this, right? You're going to F1, and let's say you're one of the participants, and you show up, instead of in a Ferrari, you show up in a pickup truck. Okay? You've got the most power, but that power is not designed to do what you want to do. And you'll see that here. I'll keep using this analogy so you can kind of understand how performance and application types, how do they relate. So here we have a pickup truck or a truck, and you basically, that is similar to all your large flows. You think file transfers or backups, right? Or replication. Things like that. That's large amounts of data going across, and they generally don't have latency requirements. What they want is high throughput. There was one gentleman here that I just spoke to, and he was talking about how do we get to maximize throughput. And one of the key things is first figure out what is your application. Is your application actually capable of leveraging the full throughput? Then you start talking about, okay, so how do I optimize it for that? Now, as I mentioned, backups, log files, and so on, these are some of the larger flows. And then you have smaller flows which are more latency sensitive. And this is where our telco brothers, and their applications are all small packets, often a few hundred bytes. And they want the lowest latency possible. In a previous life, I was also in I was helping with high-frequency trading applications. Those are the kind of applications where you're literally looking at nanoseconds. I want to use a 1-meter cable instead of a 5-meter cable. If you're thinking in those terms, then that's a completely different world, okay? But once you've crossed that world, this is still low latency, but it's not the same kind of low latency. Those things, those small flows, and sometimes, so not only HFT, one of the things that we're noticing is messaging applications are also small packets, and they're also latency sensitive. And this is what we keep saying, in present days, right? So if you have something like that, in-memory databases, things like that, those are more latency sensitive. Now, when it comes to, as I mentioned, large flows equals to high throughput. There's no question about that. Think about it this way. If you want to move a whole bunch of groceries, right, from one country to another, it's easier to send it through a truck because there's one checkpoint, one check, you're done. Versus if you had to go through, use a Ferrari or something like that to send it, you have hundreds of checks because you are sending it in hundreds of cars, right? It's the same thing here too. With larger flows, you get high throughput with very little CPU impact. With smaller flows, smaller packets, the impact is all on the CPUs because the CPUs need to process every single one of those packets, okay? Now, how does that relate from a latency point of view? Our friends from telco, they would like to see really low latency, and the expectation is, hey, every packet should have the latency that I want, and that low latency, and so on, right? But the reality is, in real world, that is not how it works. The problem is just like on the roads, where you have different cars and different sized trucks all on the same road. On the network side too, unless you design it correctly, where you're separating your latency-sensitive apps, especially the latency-sensitive apps, right, away from every other application that you have, like your backups. In reality is, in real world, you have this situation. You have a huge truck, you can't go anywhere. You are stuck with the speed that truck basically provides. Any large flow can significantly impact your latency-sensitive traffic. And this is true across the board, nothing to do with NSX, okay? This is true, again, in a previous life, working with Cisco, I had an opportunity to test with, buffering and all that. And the moment you hit a large flow, your latency goes off the, it could be a millisecond or nanosecond switch, but your latency goes off the board once you hit large flows. You're all with me still? Okay. All right. So what is the role of hardware in this performance, right? We've seen what is throughput, what is latency, how the applications work differently between these two. When it comes to, okay, maybe I should turn to this side and do it. From a NSX platform point of view, some of these things like switching, routing, and firewalling, right? These are all basically they leverage what we have, TSOs and LROs and things like that, which is large. They work on large segments. Let me pause there for a second. How many of you come from a pure traditional physical fabric networking point of view? Networking, not server, networking. Okay. So for you, it may be a shock. If you see, if your MTU is set to 1500, you get 1500 byte packets, or rather, a little bit here and there. But you would not see a 9,000 byte packet or a full large segment of 64,000 bytes. Within the system, NSX networking, switching, routing, firewalling, what have you, right? Those are all actually looking at large segments, 64,000K segments. And that is how we decrease the CPU impact on these large flows. But then you do have some other applications, for example, IPsec or TLS, or these flows. You have to go through every single byte of that packet to actually process it, right? That is where you basically end up hitting the CPU. You follow that, right? On one side, on this side, with switching and routing, you just look at the header, and you're good to go. On the other side, you're actually looking at the entire packet. The moment you start looking at the entire packet, that means that is the cost that you have to expect from the CPUs. And so on this side, faster CPUs help. But on this side, it doesn't matter. Okay? So knowing what you want to use and how you want to use it also really matters. Okay? CPU cost. On one side, it doesn't matter at all. So based on your application use. Okay. With that, let's go to queues and offloads. I'll kind of quickly go through this. This is what I was talking about, the Geneva offloads and RxTX filters and so on. One of the easiest ways to improve throughput, right, is to increase the MTU. size. Now the MTU, not just at the ESXi level, but also at the VM level. So you could set the ESXi level to 9,000, but if your VM is still at 1,500, it's only going to send 1,500 byte packets. Okay? Within the system, based on TSO, there may be a little difference, but generally, like if you want to have higher throughput, then you have to change it all the way at the workload level. Now, once you change that, in all cases, like we go with 8800 to give you that buffer for the overlay when you go 9000, 9K package size, right? And then you see a huge throughput difference just by changing that MTU. And the reason is, part of the reason is, you're not processing the entire payload. So that basically is what helps here. Okay, again, truck and Ferrari analogy. The second thing is, this one is important, and most of the session we are going to focus on this part, but imagine you have a single lane highway or something like that, right? Or a single lane border control, right? Everything gets basically blocked there, right? That becomes your bottleneck. And it's the same thing with the systems too. If you want to change that, you end up having multiple gates so that you can have multiple flows coming through. On the system level, this is what we call the RSS queuing. RSS queuing is basically, do you use one core and one CPU to process these packets, or do you use multiple cores and multiple CPUs and multiple vCPUs to process these packets? As you can see right there, right, you will find a difference in based on how you set this up. By default, almost all systems use one queue and one core. Actually, ESXi on our side, we've been tuning this for the past 5 years. By default, when you install ESXi and then NSX, we tune this for you. But this is one area that you might want to check, like when you change drivers or things like that. Hey, is this still one queue, or is this using multiple queues? Okay, makes a huge difference. Now, there's two types of these queuing. One is the RSS, and the second one is the GNU RxTX filters. Both of them are queuing. The difference between the two is one is at hardware level, RSS is at hardware level, and then GNU RxTX filters is actually at a higher level where the ESXi can look at all the flows and see, hey, this is where I need queuing, and basically give tuning for queuing for the workloads that need it. So this is a more intelligent way of doing the same thing, the queuing. Okay. Now, again, benefits-wise, yes, once you go, RSS and RxTX filters queuing is huge from a performance impact point of view. So this is one thing that you have to take a look at. Okay, TSO and LRO. This is GNU offload. GNU offload, you imagine like this, right? Like a truck comes in, within the ESXi system, it's a truckload of payload going through the system till it hits the physical fabric. Once it hits the physical fabric, you're on whatever is the MTU, 1,500 bytes. Once that is done, you're on the other side. Again, you come back to a full LRO, right? Which is, again, a full truckload within the system. That is, whether you're sending traffic or you're receiving traffic within the system, we're looking at really large payloads. And how does this work? When a VM sends traffic, right? Large flows, by default, if the application is small flows, that's a different story. But large flows, we basically take that 64,000 payload, whatever, send it all the way down to the NIC card. And again, this is what I was talking about earlier. Almost every NIC card out there will generally support this. Okay? No matter what card you have, should generally support this action of taking that 64,000 bytes and dividing it into a payload that actually can go on the physical fabric based on the MTU that you have on that fabric. That is the job of the NIC. And because it's done by the NIC card, you save on the CPUs. And you save on processing too. Instead of processing 40 packets, you just process one, and you're done, right? So the same thing happens on the reverse side too. It's called the LRO. And LRO, generally, you'll not find a bunch of cards supporting LRO. That's okay, because LRO is not as deterministic as TSO, because basically the card has to wait and make sure you get a bunch of packets, and then you have to combine them. And just imagine, the moment you start waiting, you're increasing the latency, right? TSO is not like that, right? So because of that, LRO is not that essential, but if you have all day long just large flows, right? We do LRO in software, which is what I'm showing you here. The hypervisor does the LRO, and that still helps. And LRO, you may not see 64,000 bytes, but you would definitely see 32,000 byte segments flowing through. And it does have certain improvement. It's almost like 50% when you have offload versus non-offload. Again, be sure you understand this, right? The application needs to be an application that can leverage this throughput. Otherwise, this won't make sense. If your application is only sending small packets, then it doesn't matter. And we'll look at what to do in that case, too. OK, one last thing. The CPU speed and the CPU style, the CPU family matters too. This is one of the tests that we've done with Intel, and what we've seen is just by changing the CPU architecture, you are actually able to get another 50% out of the system. So just be aware, older CPUs may not have the same performance as the newer generation CPUs. OK. Some critical hardware features, like for these different things, like if you have large flows, you're looking at the NIC features. And the NIC features are RxTX filters, or at least RSS. And then you have the offload, TSO, LRO for Geneve. And then MTU is a fix-all, OK? If you can manage MTU, not everybody can manage MTU. Actually, let me ask, like, how many of you are on Jumbo MTU? And I mean 9,000. OK, that's good. That's good. This is not something that everyone can do. But if you can, that's one way to go. All right. For smaller flows, NIC features still matter. Geneve RxTX filters and RSS. This is key, no matter which side you fall on. OK, RSS or Geneve RxTX filters. But what else matters is the CPU, the kind of CPUs that you have. Are they faster, more cores? Is basically a better proposition. With that, I just want to quickly pass this, but basically the system itself, you can do 100 gig with no issues at all, like all through the stack within the compute, and also when you use bare metal edge, you can get to, actually you can pass 100 gig, go beyond 100 gig. There's a white paper if you look for it. There's a white paper on what we've seen from a performance perspective. And what matters is what we have here, MTUs, offloads, queuing. On the bare metal edge, you need to be very specific about the hardware that you're using, but you can get this. OK. With that, this is the meat. OK? This is the queuing part. This is the meat, especially the telco folks and anyone else who is like really concerned about the performance point of view, right? Please, this is where we go into the meat of this particular slide. So we're talking about queuing. We're talking about how border control or whatever, right? Like the more gates you have, the better your performance is, right? If you have 10 gates, but one person processing it, that doesn't help too, right? You need 10 gates and 10 people processing it. It's the same story here too. Just by increasing the queues, it's not going to help. Let's say you get some XPPS based on your CPU architecture, the kind of PNICs you have, the physical NIC you have. Let's say you get X number of packets per second out of the system. That's the processing that you can get all the way to the VM, because that's the gating factor, right? Like if you get only X here, you're only getting X at the VM level too, right? You start increasing it right down at the PNIC level. But here's the problem. Let's say, that's funny. OK. I didn't see that move till now, but anyway. Has it been doing this all the time? All right. OK, let's say you have, you increase the PNIC by about 4 queues. OK? That doesn't really solve your problem. This is at the ESXi level, at the PNIC level. But that doesn't solve your problem. Why? Because when you go up the stack, you still have a bottleneck there. You still have a bottleneck at the VNIC side. You still have a bottleneck at the VM side. But from a tuning perspective, this is the right thing to do. You start from the ESXi layer, and at the ESXi layer, you're basically saying, these are the number of queues I want. And by the way, here I'm just using 4 as a representative thing, but the cards today, they have like 32 queues, 64 queues, and so on. So you have a lot of queues available. You may not be leveraging those, okay? So once you start increasing the queues, you don't stop here. Most of the folks, they would increase the queues and think life is good, but that's not true because you still have a bottleneck. There's only one person processing this, or one vCPU processing this. So you start increasing the queues at the next layer, that is at the VNIC, like you basically say, hey, I want to leverage these queues and be able to use it at the VM side. Again, that is not the end of the story because you still have one vCPU processing this, and that becomes the bottleneck. So the final thing is you increase the vCPU count too. Now, this particular example, I'm talking about Edge VM, where you basically can get like 2 vCPU, 4 vCPU, 8 or 16 vCPU form factors, right? But even when you're dealing with your own applications, especially the telco folks, right? Your NFV applications or whatever, right? Like which are packet processing focused applications, you can still leverage the same thing. Basically, tune everything all the way to the top, and then figure out like how many vCPUs you need for the amount of packets that you're getting. Okay? And these are the different things that you can tune. Like, I mean, these different parameters that you use to tune those things at the ESXi and the VM level. Now, once this is done, this is the second part. So let's say you've used up all the queues that you can get from that PNIC. Okay? What do you do next? Increase the PNIC. This is how you scale. Someone was asking about how do we scale, right? This is how you scale. And there's one more aspect that's coming up like right after this, but this is how you basically start increasing the number of queues to get to the next level, right? And again, you have the same level of throughput, packets per processing, and so on if you tune it the same way. One last thing here, you also need to avoid inter-NUMA communication because that also can become a bottleneck, especially in the older systems, and especially when you're looking at like over 100 gig and stuff like that. So I would decrease that inter-NUMA communication, keep them separate as much as possible within the system, and that is how you get the best performance out of that system. Okay? Now, one thing is ESXi is designed to do things automatically in a way that optimizes performance. Now, the problem with that is sometimes it would take a VM and say, hey, you're using way too many resources, let me move you out. And you may want queuing for that system, and then that VM is out of that queuing. The last bunch of those couple of commands, they basically are saying, don't move the VM. I know what I'm doing, okay? I need queuing for this VM. Don't move it, leave it there. And that basically sets it up for that queuing so you don't lose the queuing portion of it. All right, and then finally, just to call out what the example that I've given is a Broadcom example, but it's the same command. Just replace it with the driver that you need, Mellanox or Intel or whatever, what have you, right? And you should be able to still do the same thing. Okay, now vCPU count. How many CPUs are you using for these applications? It's very easy at the VM level, because it's just the count of the vCPU, the count of the edge VM sizing that you use. That's just a simple table of what edge you used and how many vCPUs you're going to end up using. The more tricky part is to count the vCPUs at the PNIC level. And this is where it depends on the number of queues that you use. Don't be too focused on the queuing numbers that I used here. It's just an example. But based on the number of queues that you're using, that is the vCPU count you end up having. Okay? I'll leave it for a second. I think you should get all these slides, so don't have to worry. But anyway, with that, this is an example with Broadcom. How would you tune this? And basically with enable RSS. RSS, you get like a limited number of engines, like 2 or 3 engines. And then you say, for my VM, use RSS. But there's one more thing called DRSS. DRSS is basically available for all the workloads on that particular ESXi host, and it's a default RSS. So you can leverage either of those. End of the day, the point you need to be aware of is to actually leverage queuing. Okay? It doesn't matter whether it is RSS, DRSS, or RxTX filters. RSS, DRSS is for edge and other workloads that may not be on NSX. in the sense on the NSX network itself, overlays, but RxTX filters is for those on the NSX networks. Okay, what matters? Again, at the ESX level, PNIC, and what kind of features you have, RSS, DRSS, and so on. And yeah, number of vCPUs, that matters to the processing side. On the VM side, vCPUs, and also some VNIC tuning, RSS queuing, TX queuing, and so on, and buffers too. Buffers for to ensure, like, there's no packet drops. All right. With that, VM Edge, generally the performance, these are conservative numbers, okay? But you should be able to get like a lot more than this. This is on like older systems, normal CPUs and stuff like that. You'd be able to see up to 20, 25 gig easily with a VM Edge. Again, with like flows that are like large flows and so on. This is with iPerf. I didn't put that down, but basically any large flows, you should be able to get 20, 25 gig easily on the VM side. Now, let's go to the last section of this, the data path scaling out and so on. So we have 3 stacks. We kind of like briefly spoke about this in the beginning. The standard data path stack is what you all are probably using today, and this comes by default. And this is good for like bandwidth heavy applications. This is good. This is still good for latency too. But if your applications are all latency focused, that is where for telcos and so on, right? You go with enhanced data path. Let me ask this question again. How many of you are actually using enhanced data path today? Okay, 1, 2, 3. Okay, so, and that percentage actually reflects in the real world too. Like it's a very low percentage of folks who have the applications that can take advantage of this. But that might change as we keep going forward, right? As applications go faster, that might change, and you may be here too. With the, you need to change stack for this one. And of course, finally, the data processing units, the smart NICs and so on. Of course, that'll save your CPUs and everything else too, right? Okay. With that, let me quickly talk about like scaling from the host perspective. These are the numbers for one host, right? The segment T1, T0, that's one ESXi host. That's about 100 gig out of a host, right? How do you scale this up? You start increasing the number of hosts, right? Like just imagine the amount of throughput that you're getting out of this, DFW and things like that. If you leverage it, what you're actually being able to leverage from a performance perspective inside the system. How do you scale out the edges? Edges are, again, you can increase the number of edges too. 100 gig is not the limit here, but you can go up to 150, 200 gig. I think that's there's a white paper out there too. Yeah, that's another way. Again, you can scale it up based on the sizing of your NSX manager. You can scale this up too. Okay, that's from a scaling point of view. This one is again a little bit more important. Scaling out from a PNIC point of view. I kind of briefly spoke how once you've reached the limit, to increase some more, increase the PNIC, okay? But here's a little bit of math I wanted to walk through with you. When you increase the PNIC, the vCPU cost increases. And this is where I want to show this. When you have, let's say, a 2-socket system, with 48 cores each, right? Here, 48 cores is like nothing today, right? Like Intel also has like, what's like, I think the recent one was 56?
56, 60, if you can grab them.
Yeah. Right. I was thinking like more like 64 too, but AMD has like way over the top, right? 128 something. So what I'm taking here is a very conservative CPU count. With this conservative CPU count, if you have an HVM running here with 16 vCPU HVM, and let's say I tune it with 8 RX queues. RX is the one with where you need help. TX not so much, but let's say 8 RX queues and so on. You're using 20 vCPUs, but the cost, even at 48 cores, you still have cores left out, a whole bunch of cores. To really leverage the entire system, right, the best way to do it is to actually increase the PNIC count. Now, you may not be able to do it today with your current systems because it's a cost. Increasing the PNIC is not like an easy task. But when you're designing systems for future, right, you should plan on having more than 2 PNICs. Like, go with a 4 PNIC design because that will help you. In the long run, that helps you a lot better when it comes to the performance point of view. Okay. And it'll also decrease the CPU count, the host usage count, right? Like instead of using 16, you'll end up using 8. So both ways it kind of helps. And so keep track of that. And last slide, and I'm getting some marks from there, but this is the important stuff too. We were talking about trucks and fast race cars and stuff like that. So this is where rubber meets the road, kind of, right? So what matters? Okay. End of the day, the hardware matters. You can't just say, hey, this is all in software, right? Like the NIC cards matter, the CPU matters. So the overall system performance matters. You won't believe, like, when we started this off, one of the basic things we would say is most systems in BIOS have a mode where it says, do you want to optimize it for power or optimize it for performance? If you have it optimized it for power, that means you're not getting enough out of that system. That system would idle most of the time, right? So those things matter. Performance tuning all the way down from the hardware level. And then the next thing is config. How do you configure? For most of the things, we configure by default. The RxTX filters, the offloads, they're all configured by default. What you do probably have to dig into is things like RSS. Do you want 4 queues, 8 queues, 16 queues? How do you want to carve these queues up? How many for Rx? How many for TX? Where do you want the VM placed? All of those things are something that you can tune. And it should not be for every workload, but some specific workloads for, like, for example, Edge VM and things like that. Okay? Then compatibility matters a lot. Most of the issues that we see have to do with driver that was not certified, and people use them anyway, and then you start hitting all kinds of random issues. If you want to avoid issues, this is a public resource. You can go and basically check, here's my card, here's my driver, here's my firmware. Let me see if that is actually supported, right? Please make, and for bare metal edge, very clear hardware requirements on the bare metal edge installation page. So you should take a look at that. Workloads matter. Throughput versus latency. What kind of workloads do you have? Do you have, if all you have is throughput, like, large float throughput focused applications, almost 99% of you would fall under this, what you call throughput-heavy workloads, and you should be fine with those. But if it's a latency-focused application, which is what like we saw with 3 other people here, then you start thinking of, do you want to change the stack? You have options, like you can go to enhanced data path. You're not losing anything on the throughput side. It's basically best of both worlds if you go towards the enhanced data path. And for folks who are even more concerned, you can also go to the SmartNIC path too. And finally, from a design perspective, the data path matters. How do you scale out? It matters. In terms of, like, also from, like, do you want to use VM edges? Do you want to use bare metal edges? All of these different things matter. So that's basically what you need to look at from a performance perspective. And that's it. And please take this away. We have 2 minutes if anyone wants, if there's any questions. But I'll stay back here, and we can talk after the session too. But if you have any questions, all right. So just 1 second while we get the mic.
I'm sorry.
And anyone else? Otherwise, okay. Yeah.
I have a question, and this is actually regarding to the other bureaus, because you providing the guidelines for the performance for the VMs. We find sometimes your appliances, from different bureaus like vRealize operations or ARIA operations or fixed things, that they are latency sensitive and they are sending huge packets. They are not optimized. So it would be great if you could like tell them.
Optimize those too, right?
Yes,
That-
because I cannot touch them, right? Because they are appliances. Yes.
Yes. So that's a great point. Actually, there is a session on monitoring. Thank you. There is a session on monitoring. That's like right after this session. I think it's around 2 o'clock. The person who's presenting it is Dixon Lee. He's an awesome SME on this side, and he can actually help you dig into the details of like how do you monitor, how do you optimize for performance, and yes. The comment taken, and I'll take that back, that feedback, and see how we can deal with those two. So you get those two. Thank you. Thank you. Awesome.